everyone. For today's lesson, we are going to learn about what a series is and how to express a series in summation notation. Our warm-up for today, we are going to actually do in class the next time I see you. So we're going to hop right into the lesson. Our learning objectives for our lesson is for you to be able to say, I can write a series in summation notation, and I can find the sum of a finite series. So this section is identifying the sum of a finite series given a summation notation situation. So I'm going to talk about what a summation notation is. Here we go. So when the terms of a sequence are added together, so that means that instead of the terms being separated by commas, all of the terms are going to be separated by either plus signs or minus signs. The resulting expression is called a series. And a series can be finite or it can be infinite. Here's how you can tell. A finite series ends. You're not going to see any ... afterwards. This simply is 2, 4, 6, and 8 being added together. And so it comes from the sequence 2, 4, 6, 8, where there are 4 terms in that sequence, and they're simply being added together. A finite series means that you'll see a ... at the end, which indicates that it's going to continue forever and ever, following some kind of pattern. Once again, it still comes from the sequence of 2, 4, 6, and 8, but you're going to see ... at the end, indicating that it's going to, like I said, continue forever and ever. So if you see no ... we call that a finite series, and if you see ... that indicates that it's an infinite series, and eventually it'll reach infinity. Now you can use summation notation to write a series. Summation notation means that we're talking about what is the sum of our series. What number would our series eventually add up to? So we have ourselves a couple of ways for us to express it. The first one is a finite. So in a finite series, what you're going to see is you're going to see 2 plus 4 plus 6 plus 8 being equal to a couple things. First of all, you're going to see this symbol right here. And that symbol is what we call an uppercase sigma. So this is what we call sigma notation. You're also going to see numbers that are on the bottom as well as on the top. And those numbers are called indexes. They represent the position of each of your numbers. So I equals 1 indicates that we're adding the numbers, of the sequence, starting from the first term and ending at the 4th term. So we start at 1 and we end after we add together the first term, second term, third term, and then the 4th term. And then this 2i indicates our rule. So for both of these series that we have here, we have ourselves the same exact notation. If we were to add 2 to each term, we would notice that that's what our pattern is. We're adding 2 to each term in order for us to get to our next value. And our rule is just simply 2i. You could also write that as 2n or 2k. All of those mean the same exact thing. So for both of these series, the index of the summation notation is I. And so sometimes you'll see the letter K or you'll see the letter N. And all of the problems that we've worked with so far have dealt with the letter N. And you're more than welcome to just continue using the letter N. So the I, the K, and the N represent the term position. And that term position could start at number 1. We could start adding at term number 5. It just depends on whatever that bottom number actually is. Whatever the top number is, that's going to be your ending term. So we're adding all of the terms from the first term to the 4th term, or from the 3rd term to the 8th term, whatever the case may be. So whatever's on top that's the number of term, or that's the ending term position that we're going to be adding together. The lower limit of our summation for both of these is the number 1, I equals 1. So we'll see I equals 1 or n equals 1 or k equals 1. Sometimes we might start at a different number. It just depends on the situation. The upper limit of summation, that is going to be the number 4 for our finite series, and infinity, which we'll use the infinity symbol for an infinite series. That means that we are adding together all of our terms from starting with the first term and ending with the fourth term, or we're going to be adding all of our terms starting from the first term and ending at the infinite term. And so whenever we're dealing with any sort of infinite series, we have to do a little bit more analysis with it to see if it actually has a sum or not. We're not quite there yet. But summation notation is also called sigma notation. And that is because it uses the uppercase Greek letter that we call sigma. And the way that you draw sigma is, I like to draw it using like a wider equal sign and then kind of like making a zigzag in the middle. And then if you want, you can put these little tick marks on each side as well if you would like. So once again, it's like a equal sign that's a little bit longer with like looks like a sideways M if you'd like, with these 2 tick marks on each end. If you choose to use the 2 tick marks, it's up to you. So once again, I'm going to use the space up here to talk about what this represents. So sigma notation means that you're going to have your lowest position, whatever position that you're starting with, your lowest position will be at the bottom. Up top will either be your last term position, if it's finite, or you're going to see an infinity symbol if it's infinite. Then what's going to take place right here, what this big huge M is going to be eating, or the sigma symbol is going to be eating, is it's going to be our explicit rule for the sequence. You write this explicit rule without a sub n. So we're just going to write our rule, so we'll have to look at our sequence and then analyze it to say what was the rule of our series. We're going to get a series and we're going to analyze its sequence that it came from and identify the explicit rule for that sequence. All right, so let's go ahead and write a series using summation notation. Here are your 4 steps that you're going to do for each one of these problems, and I'm just going to separate each of these with a little bit of space and just write it just below. There are a total of 4 steps. Step number 1 is we are going to identify the type of the series. And what that means is that you need to identify, is this arithmetic, geometric, or neither, in the exact same ways what we did in the past. Are we adding the same number, multiplying the same number, or some other pattern occurring? So you need to make that decision first. Then step 2, once you've made that decision, you need to write an explicit rule for your series. So that explicit rule is going to be in the form of d times n plus b, or it'll be in the form of a sub 1 times r to the n minus 1 power, or it'll be one of our neither equations, and it could have anything. It might just deal with n's or whatever the case may be. And we have to come up with our explicit rule. Step number 3 is you need to identify if it's going to be, if it's finite, you'll need to identify what the last term position is. So if you have finite, identify the last term position. A lot of times you will not know what that position is. You'll just know what the last term is. So you'll be given a sub n and you'll need to solve for n. If it's infinite, then you're simply going to use the symbol of infinity. And finally, you would write your answer in summation notation. All right, let's go ahead and practice this. Let's look at letter A. For letter A, I'm going to draw a line for some space because there's not a lot of space right here. The first thing I need to do is I need to analyze the numbers. I have 4, 7, 10. To go from 4 to 7, I know I can add 3, and to go from 7 to 10, I'm adding 3. So from the very beginning, step number 1, I can tell that this is going to be arithmetic. Step number 2, I need to write a rule. So since this is arithmetic, I know what my common difference is. That's going to be 3, and I'm going to choose an ordered pair that I know is easy. I'm probably going to work with 1, 4. Now that I have my common difference and my ordered pair, I'm going to plug it into my rule, which is a sub n is equal to d times n plus b. And a sub n is going to be 4 equals d, which is 3, times 1 plus b. I'm going to now solve for b, and I'm going to subtract 3 on both sides in order for me to find that b is equal to 1. So now my rule is a sub n is equal to 3 times n plus 1. So now that I have my rule, next thing I need to do is I need to identify, since this is finite, we have ourselves an ending term, I need to identify my term's position. Notice that we have 4, 7, 10, that's the third position. Then this dot, dot, dot indicates that we've got a few more numbers in between, and then 46. So I need to know what position, how many terms are there, what position is 46 in? Is it the 10th term, 11th term, 12th term? We need to figure that out. Is it the 100th term? So what I'm going to do next is I'm going to let a sub n equal 46, and I'm going to find n. So I'm going to write 46 is equal to 3n plus 1. I'm going to subtract 1 from both sides, and I find that 3n is equal to 45. And dividing both sides by 3, we find that n is equal to 15. So our summation notation, which I guess I need just a little bit more space. My summation notation is going to look like this. This is step number 4. I'm going to draw my equal sign. I'm going to write my rule, which is 3n plus 1, and I'm going to write it without the a sub 1, or without the a sub n, and then I'm going to say that this is the sum starting at the first term, so I'm going to call this n equals 1, going all the way up to 46 is in the 15th position, so it's going to end at 15, and I've just written summation notation. This is for a finite series. Finite series requires a little bit more work than an infinite series, and let me show you the reason why. Let's go ahead and look at letter B. For letter B, we have ourselves a dot, dot, dot at the end. Okay, cool. So now let's go ahead and identify our rule. So I'm going 1 plus 1/8 plus 1 over 27 plus 1 over 64. Well, clearly this is not arithmetic or geometric. This is a neither situation. So I'm starting off with this being a neither. Next, I'm going to look at my term position. This is a 1, a 2, a 3, and a 4. This is the first, second, third, and fourth position. And I know that if I were to make this 1 over 1, that's 1 to the third power, 2 to the third power, 3 to the third power, 4 to the third power. So my rule is going to be a sub n is equal to 1 over n to the third power. So now that I have my rule, and I know that this is infinite, so I'm just going to have an infinity symbol at the top. My summation notation is going to start with n equals 1, because 1 is my first term. We assume that the first number that's given to us is our first term. It's going to end at infinity, and my rule without the a sub n is 1 over n to the third power. And there's your summation notation. There's nothing further for you to do. So I'm going to erase this line to give myself as much space as possible for letter C. What I would like you guys to please do at this time is please go ahead and pause the video and try letter C and letter D on your own. See if you can handle these problems without my assistance. And then when you have an answer, please go ahead and restart the video and we'll see how well you did. All right, let's go ahead and see how well you did. So the first thing you need to do is decide, is this arithmetic, geometric, or neither? So to go from 7 to 14 and 14 to 21, we're adding 7 each time. That tells me right away that this is going to be arithmetic. So my common difference in this case is going to be 7. So I'm going to use the ordered pair 1, 7, and I'm going to plug those values into my rule for an arithmetic sequence. And that is a sub n, which is 7, is equal to 7 times my n value, which is 1, plus b. So I need to find what my b value is. 7 times 1 is 7. I'm going to subtract 7 on both sides, and I find that b is equal to 0. So my rule is going to be a sub n is going to be equal to 7 times n. If you want to write plus 0, you're more than welcome to, but you don't have to. So that is step number 2. Step number 3, because this ends at 77, this is finite, I need to figure out in what position is 77 located. So I'm going to let a sub n equal 77. So I'm going to write 77 is equal to 7 times n. Dividing both sides by 7, we find that n is equal to 11. So now that I know that 77 is in the 11th position, this tells me that I'm going to be adding together a total of 11 numbers. So I'm going to write n equals 1 at the bottom, and I'm going to end at 11 on the top, and my rule was 7n if I were to write that without my a sub n. And this is my answer. This is summation notation. So hopefully you did pretty well on that, and it was kind of easy for you. If not, make sure that you let me know the next time I see you. For letter D, looking at, we have to identify is this arithmetic, geometric, or neither. So we're going from -4 to -8, -8 to -12, -12 to -16. And it appears as if we are subtracting 4 each time in order for us to get to our next value. So once again, this is arithmetic, where our common difference is equal to -4. And I'm going to work with the ordered pair 1, -4, and I'm going to plug those values into my rule for an explicit arithmetic sequence. So I'm going to write -4 is equal to -4 times 1 plus b. -4 times 1 is -4, so I'm going to add 4 to both sides, and once again we find that b is equal to 0. So our rule is going to be a sub n is equal to -4n. Now, since this is infinite, we know that it's infinite because it ends with a ... That means I'm going to end up with an infinity symbol on the top. So I can just go straight to writing my summation notation. So I'm going to write n is equal to 1 because I'm starting with the first term. We assume that -4 is the first term. It's going to end at the infinite term. We don't have an ending point. And we're going to use the rule -4n. And that is our answer. So hopefully these weren't that bad for you. Like I said, if you're struggling with this idea of writing a series in summation notation, make sure you let me know. But one of the nice things about summation notation is that if you're adding 100 terms together and you're trying to express the sum of it, it kind of condenses all of those terms down, because otherwise it's going to appear as if you're adding a ton of numbers together. So what we want to do now is we want to actually find the sum of our series. So what we need to do is we need to take all of our values, or we need to figure out what values we are actually adding together. So in this first problem of letter A, we want to find the summation starting at the third term. Let's have it clear up so you can actually see it. We're going to start at the third term, and we're going to end at the fifth term. And so what that means is that I'm going to add the term that's in the third position, the fourth position, and the fifth position together. So I'm going to let K equal 3, 4, and 5, because those represent our positions. And I'm going to substitute those values into our rule in order for us to come up with the terms in those actual positions. So I'm going to sincerely plug in 2 minus 3 times 3, and that's going to tell me the number that's in the third position. And I'm going to add it to the number that's in the fourth position. And I can find that number by going 2 times 3 times 4. I'm going to find that number and add it to the number that's in the fifth position. And I can find that number by going 2 minus 3 times 5. So 2 minus 9, that is equal to -7. Plus 2 minus 12, that's equal to -10. Plus 2 minus 15, that's equal to negative 13. So the terms that I'm adding together are negative 7 plus negative 10 plus negative 13. They would be a part of my finite series and they're part of the sequence negative 7, negative 10, negative 13. So this is my series that I'm adding together, and if I were to add all of these numbers up, I would end up with negative 30. So the sum of the series starting at the third term and ending at the fifth term is equal to negative 30. Let's go ahead and look at letter B. Letter B says we want to find the sum of the terms starting with the fourth term and ending at the eighth term using the rule k squared minus 6. So I'm going to let k equal 4, 5, 6, 7, and 8. So I'm going to substitute all of these numbers into my rule in order for me to identify each individual number that's a part of this series. So I'm going to go 4 squared minus 6. That'll tell me the term that's in the fourth position. And I'm going to add it to 5 squared minus 6. And I'm going to add that to 6 squared minus 6. And I'm going to add that to 7 squared minus 6. And then finally 8 squared minus 6. So I'm going to add all of these numbers up, and I'm going to identify each of those individual numbers. You're more than welcome to put all of this into your calculator exactly as you see it, but you kind of want to make sure that you avoid making errors. So I'm going to try to identify each part individually and then add them together. So 4 squared is 16, and 16 minus 6 is equal to 10. 5 squared is 25. 25 minus 6 is 19. 36 minus 6 is 30. 49 minus 6 is 43. And 64 minus 6 is 58. So I'm going to add all of these numbers up, and together they end up adding to 160. So the sum of this series starting at the fourth term and ending at the eighth term is 160. Let's go ahead and have you guys try letter C on your own. Please pause the video and we'll see how well you do. When you're ready to go, restart it, and hopefully you're going to do pretty well. All right, so for this problem, I want you to let n equal 1, 2, 3, 4, 5, 6, 7, and 8. And plugging those values into our rule, I have 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared. And that is really adding together 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 plus 64. And if you were to add all of those numbers up, you would end up with the number 204. And that is the sum of our series, as well as the end of this lesson. If you have any questions over summation notation, how to write it, and how to interpret it, please make sure that you have a conversation with me as soon as possible. Otherwise, I hope you have a wonderful day.